Alice and Bob are playing a game where they start out with an initial configuration of n boxes where n can be up to 20, and each of these boxes have an integer written inside of it. Suppose the integer over here is a, this is b, and this is c. Now some of the indices are special, and you will see that they are encircled with a yellow circle. So these indices, not the boxes but the indices, they are known as a portal. And the rules of the game are that in one move, whoever's turn it is, they can select one portal and delete the number that is written on the box corresponding to that portal. So this configuration, after this configuration, this B will be deleted and this box will become empty, and then you have to concatenate this, like C will migrate towards the left. So you have to fill the gap by migrating towards it. So you can see that if you start out with the configuration ABC, then if you want to use this portal in the first round, then in the next round, the configuration becomes A comma C, and now you are allowed to delete C because now C is also inside a portal. So you can see that by the rules of the game, in one round, you will remove exactly one element. So in a total of n minus 1 rounds, there will be, after a total of n minus 1 rounds, there will be only a single element remaining. So Alice and Bob are playing this game, and Alice is trying to maximize the value of the last element that remains, and Bob is trying to minimize that value of the last element that remains. So your goal is, given an initial configuration of the boxes as well as location of all the portals available to you, as well as the numbers that were written on the boxes originally, you have to find out if both Alice and Bob play this game optimally, what will be the last element that would remain. How do we solve this very vague game theory problem? So if you see this problem in a contest, you most likely will skip it because you don't even know where to start thinking about this. One idea that you might get is n is less than 20. So this problem definitely has to involve Bitmask somewhere, because 2 to the power 20 is roughly 10 to the power 6, which is within the time bounds for problems used in competitive programming. So whenever you see n around 20, some form of Bitmask is usually involved. But how do we apply bitmasks when the numbers are positive in the integers? Like, how do you encode those large integers? It is simply not possible. So even if you are not able to solve this problem, but if we see this constraint that n is less than 20, let us try to solve a simplified version of this problem where we can actually apply the bitmask. So we actually don't know what to do with the bitmasks right now, but we have some guess or some intuition that bitmask should be applicable one way or another. But bitmask can only be applied if you have a binary array containing zeros and ones, but here there can be bigger number as well. So why don't we focus our attention on solving the problem when the entire array contains either 0 or 1? So let's look at the simplified version of that problem. So in this version, let's say this element is 0, this is 1, this is 1, this is 0, this is 1, this is 1, 0 and 1. So since n is less than 20, then if you concatenate all the elements and assuming each element is either 0 or 1, you will get a binary string. and this binary string will have a decimal value, and you can call that as a mask. So this is a very common theme in Bitmask related problem, that you view the big binary string of length 20 as a single decimal integer to simplify things in your head and to do some DP related optimization. Now we are interested in finding whether this bitmask, like the bitmask that you see on the screen, in this bitmask, who will be the winner? Like your goal, so Alice's goal is to have the maximum value remaining at the end, but there can only remain two values at the end. It can be either a 0 or 1. So you can see that Bob will try his best to ensure that a 0 remains at the end, and Alice will try her best to ensure that a 1 remains at the end. So if I define something like dp of mask, dp of mask, and let's say dp of mask represents the final value at the end. Final value at the end. Now you will see that this dp of mask, the reason why I am defining it like so is because once you do this operation, so you have started out with a number with 20 bits, and after doing this operation, suppose you decide to use this portal at index 3, then the resulting number would be what? 0, 1, and this 1 will vanish and you will have 0, 1, 1, 0, 1. So you are now interested in finding out the answer when you start the game with this configuration. So it makes sense that one mask transitions to another mask, right? The game can only go into a series of masks like M1, M2, M3, and so on. So the DP definition will definitely have a mask parameter there, and mask encodes this entire binary string. And you can notice that since we are dealing with n less than 20, there can be only 2 to the power 20 different masks that can be created out of this game, which is 10 to the power 6 roughly. So that's why if you define this DP definition, we should be able to solve this problem. But let's see whether this DP definition is enough or is it missing something. So if I ask you, like, given this mask, what will be the final uh, element that is remaining? Or maybe I'll simplify the problem a bit for you. Given this mask with a single integer 1, can you tell me the final integer that is remaining? Is it 0 or 1? So it is not possible to infer with just this mask because you don't know whose turn it is, whether it is Alice's turn or whether it is Bob's turn. And depending upon that, you will change the strategy, because if it is Alice's turn, she will try her best to make a move that will ensure that the last element available is 1, but Bob will do the opposite. So this means that this DP definition is missing something in its parameter, and that parameter is whose turn it is. So let's modify this DP definition. And now this time, let's keep it something like DP of mask and who. And this who will represent whether it is Alice's turn or Bob's turn. Now let's see whether this DP definition is sufficient to gather all the information that we need to do the DP transitions. So if you have a mask, like let's say 1, 0, 1 1, and you have all zeros over here. And suppose the portals were located at this index, this index, this index, and this index. Now, and since we are now also maintaining the who parameter, like we know whose turn it is, whether it is Alice's turn or Bob's turn, Alice or Bob. Now, if I just give you this information, I tell you that, okay, this is the game configuration that you have reached after some number of steps, and Alice is about to make a move. Then can you figure out what will be the last element remaining? Or is there some information that is missing, that is not letting you compute the answer? So you will see that if the game has reached this stage, then it means that you must have already used some portals. So this length might not necessarily be 20, it might be less than 20. But if these are the leading zeros, then so 0 was a valid initial element, right? So looking at this 0, how do you figure out if you have already used the portal at this location and then removed this element, deleted this element, or you have not used this portal at all? Because 0 doesn't mean that you have deleted that element, because 0 was the initial element that was already present in some of the portals. So suppose this portal contains 0, so if it contains 0, doesn't mean that we have deleted it, because if you have deleted it, then you should have removed this 0, and then you should have slide in all the numbers on the right hand side to the left. So this means that the leading zeros that you have for a given mask, that can be a bit confusing, because that will not tell you the reality of whether a portal that is present in the leading zero, whether that has been used or not. So this means that we also have to maintain another parameter in the DP that that tells us what is the length of the uh, length of the initial array that you started with length n, and every time you make a transition, the length will decrease. So at a particular mask, suppose that length is L, so you also need to keep track of this L. So dp of mask L and who. So how will this L help us? Because if we know that the resulting array the resulting array only contains L elements at this transition state, then we know that we can only use the portal. So suppose this is L, so we know that we can only use the portals in this area, not the portals in this area. So this is how you can handle the leading zeros. But now that we have added this L parameter, do we really need the third parameter, like whose turn it is? You'll realize that you don't actually need to explicitly track the third parameter, because if you know what bitmask length you are at, then using its parity you can figure out whose turn it is. Because if you are at L is equal to n, then definitely it must be Alice's turn, because this is the start of the game. But if you are at L is equal to n minus 1, it must be Bob's turn. If you are equal to L is equal to n minus 2, it must be Alice's turn. So this means that just by looking at the parity of n minus L, you will be able to figure out which person's turn it is. So this means that to solve this problem, you only have to track two parameters. One is what is the mask that has been created so far, dp of mask, and what is the length that you should look for, because the leading zero can be misleading. So these two states, you will notice that they are actually sufficient to do all the transitions. But how exactly will we do the transitions? Let's look at it by an example. So suppose the game is going on and the game has reached a mask like so. Let's say the mask is 1 0 1 1 0 0. This is the game, and this is the mask that has arrived so far. And also assume that there is one leading 0, but the L that you are tracking, let's say this L says that it is equal to 6. This means that even though there is a portal over here, even though this is a portal, this is a portal, let's say this is a portal, this is a portal, and this is a portal. So if L is equal to 6, it means that you should only be looking at this block, because when you have reached this mask, then you have already deleted all of these elements. So all of the elements that got deleted, so everything got shifted towards the left. And by the way, I am doing the indexing from left to right. So this is 0, this is 1, this is index 2, this is index 3, index 4, and index 5. Because for binary strings, of course, you do the indexing from right to left, right, from 0 to n, because it kind of fits the standard binary representation. So once again, reminding you that the indices of the portals are fixed. So when you delete an element, then everything that is like this elements and this element gets concatenated together. So this portal will become active again with the new element that has arrived into it. Okay, so far so good. Now, how do you do the transition? So you know that with this L is equal to 6, you can infer that you can only use the portals from here, here, and here. And using the parity of n minus L, you can figure out whose move it is. So suppose it is Alice's move. Then Alice can take this mask, and her goal is to get a 1 at the end. But doesn't mean that she has to be greedy right now. She can explore all the possibilities. So let's label the portals as P1, P2, and P3. So Alice can try all the three strategies. That is, try to try to delete the element at P1 portal, try to delete the element at P2 portal, and P3 portal. So once she deletes the element at P1 portal, what is she interested in knowing? So you will notice that after you have deleted this element at the P1 portal, the mask that will be created would be 1 0 1 1, and this 0 will be deleted. So this will be the mask that will be created, and the length will be L minus 1, because you can now only future DP transitions can only touch these indices. So with P1, so with after deleting P1, you are interested in the transition of DP of, like, let's say new mask, and this is L minus 1. And how do you create this new mask? So either you can apply some fancy bit manipulation trick, like your goal is to, how do you effectively erase one bit from a mask? That is what you want to achieve. So there are very fancy bit manipulation tricks to do that. I will not go into the tricks in this video, because if you don't want to use any fancy tricks, it's very simple. You just iterate over, you make a copy of this mask, and then you delete that element, and then you'll get a new mask, and you are done. So a lot of people, I see that they skip bit manipulation tricks, bit manipulation problem, because they don't want to use any of the bit manipulation fancy trick, like setting a particular bit, or using some fancy OR technique, or unsetting a bit using some XOR technique. all that is fine. If you don't want to use those fancy tricks, you can still, at the end, this is still a binary string, right? So you can still iterate over it manually and then delete whatever element that you want to delete, and then construct the new mask again, because using the like this is just a binary string, so you can just convert it to a integer. Now what happens if you delete the portal at p2? Then the mask that you will get would be 1 0, and this 1 will vanish and you will have 1 0 0, and you are now looking for this smaller length of 5, right? So you will now look for dp of this mask with the length as 5. And for p3, if you delete this p3 portal, then you are looking for, if you delete this p3, then the mask will become 1 1 1 0 0. So you are now interested in the answer for dp for this mask with the length 5. Now if at least one of these dp says that the final element is 1, that is, let's say that this dp stores true if the final element is 1, else it stores false. Then if any of these elements says that the final element of these masks, starting with these masks, can be equal to 1, then then Alice should pick that choice. So if after using this p2 portal, from this configuration, if it is possible for uh, Alice to make sure that the final element remaining is 1, then you can see that Alice should use the p2 portal. So that is why Alice will have a strategy where she will do an OR of all the choices. Why? Because she is only interested in one path that will for sure lead her to the final portal containing 1. Now don't worry about the implementation details of how you would do all these concatenations and removals and figure out the masks, etc. That is not important. Important is that you understand why and how these transitions work. Now what about the transitions for Bob? So for Bob, you can see that the number of choices remain the same, because Bob can also only delete the portals that are available to it, right? There is no fancy move that Bob can do. But for Alice, you will notice that if any of these entries is 1, then the answer for dp mask of L, if it is Alice's turn, it will be 1, because we know for sure that there is at least one transition that leads to a 1. So Alice can definitely take that route. But for Bob, like if it is Bob's turn, then these are the possible transitions again. And then for Bob has to ensure that none of these transitions lead to a 1, because if they are leading to a 1, then Bob cannot prevent Alice from using that configuration and then eventually reaching 1. So Bob has to make sure, like if it is Bob's turn, so Bob has to take the AND of all the P1, P2, P3 choices, because Bob is trying to make sure that Alice doesn't do anything that will help her reach the goal. So if Bob can ensure that all these P1, P2 and P3 choices, after all of these choices the final result is still 0, then Bob can be sure, if it is Bob's turn, then Bob can be sure that from this configuration the final result will always be 0, no matter what Alice tries, because if at least one of these leads to a 1, then Bob cannot prevent Alice from taking that. So the concept that we have just discussed is known as min-max DP, minimax DP, let's say. And this is one of the key concepts in game theory, where if Alice and Bob are trying to, if Alice is trying to maximize something and then Bob is trying to minimize it, then if Alice is trying to maximize it, she will try to take one path that is favorable to her, because if it is her turn, then she controls which path she takes. But when it is Bob trying to minimize that particular quantity, Bob has to make sure that when it is eventually Alice's turn, then all the paths, like suppose this is the bit mask that you are at, then Bob has to make sure that all the paths lead to a configuration that will eventually land at 0, no matter what Alice does. Now the time complexity for this would be simply O of n into 2 to the power n, because there are 2 to the power, so there are, you are maintaining 2 to the power n states in your DP, and then you are also maintaining n in your DP. So the time complexity is n into 2 to the power n, and then you are also maintaining all of these portals in, while doing the transitions you are iterating over all of the portals that are allowed. So that will be an additional O of n square into 2 to the power n, like O of n additional factor. But using some number theory, you can prove that you can actually do it in O of n into 2 to the power n. But that is not the point of this video. That even if you forget about that optimization and you assume that the complexity is O of n square into 2 to the power n, at least you know that the solution is correct. So now what will be what will the final answer be? Like we have computed the DP mask for each mask from 0 to n. So 0 to 2 to the power n. So suppose this is 0, this is 1, this is 0, 0, 1, 0, 0, and 0. So you already have the answer for DP of mask and L for any L. Then to find the answer for the original game, you have to start with the mask that is available to you. So you just convert this entire thing into a mask and you write that down over here. And then what is the length of the array that you are starting with? That is simply L. That is simply N. So this value, if this value is 1, it denotes that the Alice can ensure that the final entry will be 1, but if this value is 0, it will denote that Alice cannot ensure that the final entry remains 1. And I hope you can see the transitions. So from this mask you will go on to other masks, and with the second parameter as n minus 1. So that is why if you try to memorize all the masks comma length combination, there can only be n into 2 to the power n combinations. So if you remember the results for all of them, you will see that you will solve all the possible ways this game could go. So now we have our algorithm that if we have any mask that is of length at most 20, 0, 1, 0, 0, 1, 1, 0, 0, etc. Using the algorithm, using the bitmask DP that we just defined, we can ensure, we can figure out what will the final remaining element be, whether it is 0 or whether it is 1. Now we know for sure. So we have solved the easiest version of the problem where all the array elements are 0 or 1. Now let's make this problem a bit more complicated and say that instead of having all the elements as 0 or 1, assume that the numbers could be anything, A, B, C, anything. How do you solve this version of this problem? So if you have understood till this part, then all the hard work is done. Now it's just a matter of applying some fancy tricks to reuse the solution from this part and apply it to future problems. Now, if you have this configuration, then you know that you know how to solve this problem for a 0 1 0 etc. A binary string you know how to solve using Bitmask DP. But if I give you this configuration, and like let's say the numbers are 5 9 22 33 1 2 5 1, and I ask you, if both Alice and Bob play optimally, what is the largest value that can remain till the end? Because Alice is trying to maximize it and then Bob is trying to minimize it, so we have to figure out which value will remain at the end. Now of course you cannot encode all of these numbers in a Bitmask, but one thing you can do is, even though it's difficult to answer the problem which element will remain at the end, we know that solving it on a binary strings is easy, and we have just done that. So how can we take this problem and reduce it to a binary string problem? So this is a very famous and well-known technique wherein you define, if you want to convert if you want to convert a set of integers into a binary string, so you define something as f of a, and you say that f of a is equal to, or you basically ask this question, instead of worrying about the final remaining element, you ask, is it possible is it possible to have the last element to have the last element greater than or equal to a? So if you want to have the last element greater than or equal to a, then it means that any element that is greater than or equal to a, if they remain at the end, then your condition is satisfied. But if an element remains at the end which is strictly less than a, then your condition is not satisfied. So in this example, suppose a is equal to 10. This means that in this array you ask the question, if you start with this configuration, is it possible to achieve the final value greater than or equal to 10? This means that this array element is not a candidate for being the final element, because this is less than 10. This is also less than 10, so this is not a candidate. This is also less than 10, not a candidate. This is greater than 10, this is a candidate. This is greater than 10, this is a candidate, not a candidate, not a candidate, and not a candidate. So you see that by using this different question, like we ask the question, can we make the answer at least a? We have now reduced the original big integers to just a binary string, 0 and 1s. And you will see that the problem, solving the problem on this is equal to solving the problem on this, because zeros represent the values that are smaller than a, and ones represent values that are much larger than a. This means that Alice's goal will always be to ensure that a 1 remains at the end, and Bob's strategy will always be to ensure that a 0 remains at the end, so that the final number is as small as possible. So using this question, you can convert this to a binary string. Now you will realize that this question that we just asked, this is the standard question that we ask for binary search related problem. So essentially what we are doing is a binary search on answer. So this is binary search on answer, because suppose the answer, so suppose this is the 0 and this is the max possible value. So first you split this segment in half and you ask whether it is possible to achieve the maximum at least mx by 2. So if the answer is yes, then it means that all the segments from the left half, they will also be achievable. Why is that? Like if you can create an answer with at least mx by 2, it means that you have a strategy to select some element so that the final element will be at least mx by 2. Then this part will automatically be satisfied. Why? Because if mx by 2 is equal to, like, let's say 9, then if I ask you that if you can you create a configuration where the final result is at least 9, so you say yes. And then I ask you the second question, can you create another configuration where the final element is greater than or equal to 5? So you will still say yes. Why? Because you can still use the same configuration that you used for 9. So the at least keyword, this is doing the heavy lifting, because once you have added this definition that the final result should be at least A, this already ensures that if it is at least A, then of course it is at least A minus 1 as well. So this divides this into a monotone sequence. And similarly, if you tell me that no, it is not possible to create the final element at least 9, then if I ask you, can you create a final element at least as big as 20, your answer will still be no. Why? Because if your answer is yes, then why didn't you use that same configuration and answer the same with the configuration for achieving greater than or equal to 9? So this is the one trick that is usually very common in binary search related problems. And in fact, if you define your queries of this type, that your answer should be at least x greater than or equal to x, then this by definition forms a monotone sequence wherein you will have a series of no, no, and then followed by all yes, or the vice versa. So this means that you can now solve the original problem using binary search. How can you do that? So you are given this array initially, and all you have to do is take the maximum value over here, and then uh, you have 0 to max, and you repeatedly split the segment in half and then ask the query, can you make the answer at least greater than or equal to A? And how do you solve a particular query? You convert this string to a bit mask depending upon whether each element is greater than A or smaller than A. And then once you have a bit mask, you solve the bitmask dp. You solve the easiest version of the problem using this bitmask dp. And if this says that the final element can be 1, it means that the final element can be greater than or equal to A. And then you repeat for every left half or right half. So you can see that you can already solve this problem in O of log of max value into n square into 2 to the power n, or n into 2 to the power n, whatever you want to take as the complexity for the bitmask dp that you just did. But you will notice that this log max, like if n is up to 10 to the power 9, then this can only be up till 20, so that is fine. But even if the values were up to 10 to the power, like let's say 1000 or something, or like let's say 10 to the power 10,000 theoretically, then does it mean that you have to take the actual log of this and then do that binary search? Not really, because in this problem you can do the naive binary search, but you can also notice that there are only 20 elements, and the answer has to be one out of these 20 elements, right? Because you are taking the entire element at once. You are either taking an element or leaving it. So you can just try out this bitmask. You can just try out this binary search idea by iterating from the highest order element to the lowest order element. And as soon as you hit an answer, when you are traversing in the descending order, you print that okay, I have an answer that is greater than or equal to A, but since I was iterating from the descending order, then this answer must be equal to exactly A, because this A I have chosen from the array only. So this is some binary search optimization you can apply, not that it was needed in this problem. So now we are able to solve the original problem, wherein you are given n elements and Alice and Bob can remove element from any portal, and after the removal the elements concatenate together, and this portal will now serve a new element. And we saw that you can do a bitmask DP to solve the easiest version, where you are just doing zeros and ones, and then you can apply a binary search to figure out whether the answer is greater than or equal to A. And instead of doing the naive binary search, you can just sort the array elements and then do the binary search in decreasing order, and as soon as you hit an answer, you know that even though the condition says that it should be greater than or equal to A, since you were doing it in the descending order, that has to be the answer. Now this video is already too long, but I was planning to discuss some more hard variations of this problem, but maybe I'll skip it for some another day. But before doing that, I'd like to introduce all the hard problems so that you can try it on your own. And if you do want me to make a video on the hard versions of this problem, do let me know in the comment section. I will make a video for that. So the easy version we have already seen, and the hard version says that this time you are given all the portals in advance. So all the portal indices you are given. You are also given the length of the array, but this time you are not given any of the elements. These boxes are empty. Okay, and your goal is to fill fill some integers, and each integers should be between 1 to m. So m is also given to you, which is the maximum upper limit. So each box will contain some integer from 1 to m. This will also contain the integer from 1 to m. So you can see that there are m choices at each stage. So there are total m to the power n configuration, right? So your job is to find out the answer for each of the configuration and then sum it up. So if the answer for a particular configuration is x, which means that x will be the final element remaining, so that configuration will contribute x. So you have to sum up this x over all possible configurations, where you are allowed to keep anything between 1 to m in each of the boxes. So how do you solve this version of this problem? So this problem is not difficult actually, but this is a very interesting problem, but due to lack of time, I'll not discuss it in this video itself. Otherwise, this will be unnecessarily long. So yeah, take a minute to pause this video and maybe think about how this entire Bitmask thing is working, and maybe also try to implement and submit this Bitmask DP solution, so that you know that your proof is correct and your implementation is correct. And once you are confident with this approach, then try the hard version of this problem. So this is also a very interesting problem that involves a bunch of techniques that you can reuse in future problems. So maybe one day I'll create a video on these two. So if you'd like me to create a video on this, and if you have understood all the previous parts, do let me know in the comment section. Thank you.